This is a very short lecture this morning. We are talking about torsion, and in section 3.2 we are going to quantify the angle of twist in a shaft that is being subjected to a torque. So, as I've said, the biggest engineering application for torque on cylindrical shafts is power generation, or power transmission, excuse me. But in our textbook, in order to demonstrate some of these principles without introducing the additional factor of power, which we'll do later, but we do this kind of a problem that I don't think most people would do on purpose, where you extrude a cylindrical shaft from a wall and you subject it to a torque, and then you see what happens to it. So in this case, because the end that is attached to the wall is of a fixed location, what we learned last time was that if we look at the face of our cross sections, this is just looking at it from the outside, that as we twist it, that this point moves to this point, which corresponds to subtending this arc on the cross section, and we call this angle phi, which is the angle of twist, and we call this angle gamma, which is the shearing strain. And because this arc, A prime, for the angle of twist and gamma are the same, we can see that phi and gamma are not independent of each other. And what we can actually find, there's just a little derivation here, but basically we have that gamma max, or the maximum shearing stress, is going to occur on the edge. In other words, tau, let's do this. This is right through the middle. If we were to plot tau versus where we are for a given torque, it would be a maximum on the edges, right here, and it's 0 in the middle at the center, and that the distribution is linear. Geometrically, that's very, very important, and we'll come back to that over and over again. But gamma max is going to occur at the edge, and the value of that is going to be c, which is the radius. They go back and forth with this, which kind of makes me crazy, but we'll just do it the way they do it, so that we can be in keeping. C times phi over L. And if we do a little bit more, we can see that it's equal to T times C over J, which is that polar moment of inertia, times G, which is the shear modulus. J is the polar moment, and it's either going to be for a circle or a hollow circle, or an annular space. And because we're only going to be using circles and hollowed out circles because of the symmetry. So if you look in the back inside cover of your book, you'll find that the polar moment for a circular cross section is 1/2 pi times r to the 4th, or because we sometimes call it c, here it's 1/2 pi times c to the 4th. These are identical in the author's in his symbology. But what we really see here from this equation and this equation is that the angle of twist is proportional to the torque. Okay, so angle of twist is proportional to the torque that is applied to the shaft. Right? So if we have several shafts we can say that the angle, hang on a second. This shouldn't be gamma max. That's, sorry. There, how's that? That's better. Angle of twist is equal to TC over JG. That was my mistake. And basically, that if we have several shafts, and this does occur sometimes, quite frequently, in power transmission, where these are referred to as stepped shafts, and if we have different torques applied to them, we will find that the angle of twist at the end is equal to the summation of the individual torques times the individual length divided by the individual polar moments times the individual bulk modulus or shear moduli. All right, and the last thing I want to talk to you about is something you may have encountered before, or it may be brand new information, and that's what happens at gears, when gears mesh together. And this is sort of not an assumption, but this is something you have to know to work several problems. And I would ask you to refer to page 170, concept application or example problem number 3.4. All right. Now, and I'm going to have to show you the picture, and then I'll show you what gears look like when I draw them, because they're not anywhere near as cute as this. Okay. So what happens when you do power transmission? You will often have two shafts that have gears at the end that are meshed together. And by meshed together, what I mean is the teeth fit inside of each other so that if this one spins, this one spins as well. All right? Now, why do we put gears? Well, one is because the big reason that we put gears is, and like I said, this is the best I can do with gears. So you have to make up the teeth in your mind's eye. But basically, when this one spins, this one will spin as well. But the linear distance covered here will be the same as the linear distance covered here, which means that the rotation, if we call this gear A and B, of A is not going to be equal to the rotation of gear B. So they are related by the radii. If you think about the linear distance covered by A in one rotation, let's just call it in one rotation of A. The linear distance covered by A, when it goes around once, is what geometric property? What do we call that when you go once around a circle? The circumference, right? And the circumference is 2 times pi times the radius. It's a linear measure. So in one rotation of A, the distance covered, the linear distance, is 2 pi times RA. Well, it turns out that that's the same linear distance here. But what does that mean? This is not RA, this is R sub B. So this is going to go around 2 pi RA. And so it depends on the ratio of RA to RB, how many rotations we go around. So if A goes around one rotation, because it's longer, is the smaller gear going to go around less than one rotation or more than one rotation? More, exactly. So if A is larger than B, it doesn't matter, but just to think about that, the gear ratio, A over B, determines how many rotations this one will go around. Okay? So that's factor, I'll put that down here. And if you ever read like automotive magazines, or if you work on things that have gears, that's exactly what a gear ratio is. That's all that it means. So you get one shaft spinning faster than the other. If they're the same size shaft, but you mesh them together with different size gears, if this one spins at one rate, if you have a smaller gear over here, this one will spin at a faster rate. And it will spin R of the larger gear divided by R of the smaller gear times. So if this is twice the radius of this, that means that this will spin twice as fast. If this is 3 times this will, if this is has 3 times the radius, this will spin 3 times as fast. Okay? So the whole shaft that's attached to that gear will do the same. Now the other factor about gears is that if this spins around in this manner, there's going to be a force of A pushing up on gear B, right at that tooth, isn't there? Right at the tooth where they meet. And that means that unless this gear slips, that the force of B pushing down is going to be exactly the same. So the force of A equals the force of B. That is required if the gear does not slip or break, right? So those are the two, not assumptions, but the two underlying principles when you start working with gears. So first of all, the shafts will, if they're attached to shafts, the shafts will spin at different speeds. In other words, different RPM, or different angular speed, which is omega, generally called omega. But that it's based on the gear ratio, where the smaller gear spins faster. And then the force pushing up here is equal to the force pushing down here. And then what you have is some sort of a torque, which is a force acting through a distance. And it actually turns out that the torque applied, if this is discounting friction and so forth, is equal to that force, which is vertical, times the horizontal distance, which is the radius of the gear. Okay? So in other words, the force is the same, but if the radius of the two gear are different, the torque is different on the two gears, isn't it? And therefore on the two shafts.
So is it the radius of A and B then?
It is.
I didn't clear it out there.
That's exactly right. Very, very good. It's all governed by that geometry. So it's kind of a cool mechanical relationship. So, all right, so do you guys have any questions at this point? All right. So I promised you a short lecture. I think we delivered today. Like I said, I would refer back to that sample problem on 170, and they worked through it. They worked through it on 73 and 74, but it's a very, very good problem for sort of illuminating that idea. And for homework tonight, because I know it's always about the homework with me, isn't it? This is a vodcast. Oh, I didn't put it up yet, did I? I'll get her done. I have it. Yes, I'll put both of these up. Are you guys able to access them through the vodcast, or does YouTube work better? YouTube. Okay. I'll make sure to get that done right away. Yes, Oscar sent me the embed code, and I just didn't get it done, so I'll put it up immediately. Let's see. I would like one. Let's just do one. Let's do 2 problems. Let's do 348, which is going to have that gear issue going on, and then let's just do a pretty down-to-earth problem. Let's do. Nice, right? What's that?
I mean, it's going to treat you nice.
Yes, exactly. One that you'll do, and you'll say, "I get it. I get it. Eureka!" All right, those 2 problems for the weekend, gentlemen. So.